In our previous lesson, we saw how we can implement queue using arrays. Now in this lesson, we will see how we can implement queue using linked list. Queue, as we know from our previous discussions, is a structure in which whatever goes in first comes out first. Queue data structure is a list or collection with this restriction that insertion can be performed at one end and deletion can be performed at other end. These are typical operations that we define with queue. An insertion is called in queue operation and a deletion is called dequeue. Front operation, front function, should simply return the element at front of list, and is empty should check whether queue is empty or not. And all these operations must take constant time. Their time complexity should be big O of 1. When we were implementing queue with arrays, we used the idea of a circular array to implement queue. Then in this case we have a limitation. The limitation is that array will always have a fixed size, and once all the positions in the array are taken, once the array is exhausted, we have two options. We can either deny insertion, so we can say that the queue is full and we cannot insert anything now, or what we can do is we can create a new larger array and copy the elements from previous array to the new larger array, which will be a costly process. We can avoid this problem if we will use linked list to implement queue. Please note that this representation of circular array that I'm showing here is only a logical way of looking at an array. We can show this array like this also. As I was saying, in an array implementation we will have this question: what if array gets filled? And we need to take care of this. We can either say queue is full, or we can create a new larger array and copy elements from previous filled array into this new larger array. The time taken for this copy operation will be proportional to number of elements in filled array, or in other words we can say that the time complexity of this copy operation will be big O of n. There is another problem with array implementation. We can have a large enough array and queue may not be using most of it. Like right now in this array, 90% of the memory is unused. Memory is an important resource and we should always avoid blocking memory unnecessarily. It's not that some amount of unused memory will be a real problem in a modern day machine. It's just that while designing solutions and algorithms, we should analyze and understand these implications. Let's now see how good we will be with a linked list implementation. I have drawn logical view of a linked list of integers here. Coming back to basic definition of queue, as we know, a queue is a list or collection with this constraint, with this property that an element must always be inserted from one side of the queue that we call the rear of queue, and an element must always be removed from the other side that we call the front of queue. It's really easy to enforce this property in a linked list. A linked list, as we know, is a collection of entities that we call nodes, and these nodes are stored at non-contiguous locations in memory. Each node contains two fields, one to store data and another to store address of the next node or reference to the next node. Let's assume that nodes in this figure are at addresses 100, 200 and 300 respectively. I have also filled in the address fields. The identity of linked list that we always keep with us is address of the head node. We often name the pointer or reference variable that would store this address head. Okay, so now we are saying that we want to use linked list to implement queue. These are the typical operations that we define with a queue. We can use a linked list like a queue. We can pick one side for insertion or an queue operation. So a node in the linked list must always be inserted from this side. The other side will then be used for dequeue. So if we are picking head side for enqueue operation, a dequeue must always happen from tail. If we are picking tail for enqueue operation, then dequeue must always happen from head. Whatever side we are picking for whatever operation, we need to be taking care of one requirement, and the requirement is that these operations must take constant time, or in other words, their time complexity must be big O of 1. As we know from our previous lessons, the cost of insertion or removal from head side is big O of 1, but the cost of insertion or removal from tail side is big O of n. So here's the deal. In a normal implementation of linked list, if we will insert at one side and remove from other side, then one of these operations, enqueue or dequeue, depending on how we are picking the sides, will cost us big O of n. But the requirement that we have is that both these operations must take constant time. So we definitely need to do something to make sure that both enqueue and dequeue operations take constant time. Let's call this side front and this side rear. So I want to enqueue a node from this side and I want to dequeue from this side. We are good for dequeue operation because removal from front will take constant time, but insertion or enqueue operation will be big O of n. Let's first see why insertion at tail will be costly, and then maybe we can try to do something. To insert at rear end, what we will have to do is first we will have to create a node. We have a new node here. Let's say I've got this node at address 350 and the integer that I want to enqueue is 7. The address part of this node can be set as null. Now what we need to do is we need to build this link. We need to set the address part of the last node as address of this newly created node. And to do so, we first need to have a pointer pointing to this last node, storing the address of this last node. In a linked list, the only identity that we always keep with us is address of the head node. To get a pointer to any other node, we need to start at head. So we will first create a pointer temp and we will initially set it to head. And now in one step we can move this pointer variable to the next of whatever node it is pointing to. We use a statement like temp equal temp.next to move to the next node. So from first node we will go to the second node, and then from second we will go to the third node. In this example, third node is the rear node. And now using this pointer temp, we can write the address part of this node and build this link. This whole traversal that we are having to get a pointer from head to tail is what's taking all the time. What we can do is we can avoid this whole traversal. We can have a pointer variable just like head that should always store the address of rear node. I can call this variable tail or rear. Let's call this rear, and let's call this variable that is storing the address of head node front. In any insertion or removal, we will have to update both front and rear now. But now when we will enqueue, let's say I have got a node at address 450 and I want to insert this node at rear end. Now using the rear pointer, we can update the address field here. So we are building this link, and now we can update rear. We will only have to modify some address fields, and time taken for enqueue operation will not depend upon number of nodes in the linked list. So now with this design, both enqueue and dequeue operations will be constant time operations. The time complexity for both will be big O of 1. Let's quickly see how real code in C will look like for this design. I have declared node as a structure with two fields, one to store data and another to store address of next node. And now instead of declaring a pointer variable named head, a pointer to node named head, I'm declaring two pointers, a pointer to node named front and another pointer to node named rear, and initially I'm setting them both as null. Let's say I'm defining these two variables in global scope, so they will be accessible to all functions. My enqueue function will take an integer as argument. In this function, I'll first create a node. I'll use malloc in C or new operator in C++ to create a node in what we call dynamic memory. I'm pointing to the newly created node using this variable which is pointer to node named temp. Now we can have two cases in insertion or enqueue operation. If there is no element in the queue, if the queue is empty, in this case both front and rear will be null. We will simply set both front and rear as address of this new node being pointed to by temp, and we will return or exit. Else, because we already have a pointer to rear node, we will first set the address part of current rear as the address of this newly created node, and then we will modify the address in rear variable to make it point to this newly created node. While writing all of this, I'm assuming that you already know how to implement a linked list. If you want to refresh your concepts, you can check earlier lessons in this series, or you can check the description of this video for a link to lesson on linked list implementation in C or C++. This code will be further clear if I'll show things moving in a simulation. Let's say initially we have an empty queue, so both front and rear will be null. Null is only a macro for address 0. At this stage, let's say we are making a call to enqueue function passing it number 2. Now let's go through the enqueue function and see what will happen. First, we will create a node. Data part of this node will be set as 2 and address part initially will be set as null. Let's say we got this node at address temp at address 100, so a variable named temp is storing this address. This variable is pointing to this node. Right now front and rear are both null, so we will go inside this if condition and simply set both front and rear as 100. When the function will finish execution, temp, which is a local variable, will be cleared from memory. After setting both front and rear as address of this newly created node we are returning. So this is how the queue will look like after first enqueue. Let's say we are making another call to enqueue function at this stage, passing number 4 as the argument. Once again a new node will be created. Let's say I got the new node at address 200. This time the queue is not empty, so in this function we will first go to this statement rear.next equal temp. So we will set the next part of this node at address 100 as the address of the newly created node, which is 200. So we will build this link. And now we will store the address of the new rear node in this variable named rear. So this is how my queue will look like after this second enqueue. Let's do one more enqueue. Let's enqueue number 6. Let's say we got our new node this time at address 300. So this is how our queue will look like. Okay, let's now write dequeue function. In dequeue function, I'll first create a temporary pointer to node in which I'll store the address of the current head or current front. Let's say for this example at this stage I'm making a call to dequeue function. We will have couple of cases in dequeue also. The queue could be empty, so in this case we can print an error message and return. In case of empty queue, front and rear will both be equal to null. We can check one of these and we will be good. In the case when front and rear will be equal, we will simply set both front and rear as null. In all other cases we can simply make front point to the next node. So we will simply do a front equal front dot next. But why have we used this temporary pointer to node? Why have I declared this temporary pointer to node in this code? Well, simply incrementing front will not be good enough. In this example, when I'm calling dequeue, I'm first creating temp. Let's walk through whatever code I've written so far. So in the first line I'm creating temp. And then because queue is not empty and there are more than one elements in the queue, I'm setting front as address of the next node. So my queue is good now, all the links are appropriately modified, but this node which was front previously is still in the memory. Anything in dynamic memory has to be explicitly freed. To free this node we will use free function, and to this free function we should be passing address of the node, and that's why we had created temp. With this free, the node will be wiped off from memory. So these are enqueue and dequeue operations for you. And if you can see, there are simple statements in these functions. There are no loops, so these functions will take constant time. Their time complexity will be big O of 1. In the beginning of this lesson, we had also discussed some limitations with array implementation, like what if array gets filled, and that of unused memory. We do not have these limitations in a linked list implementation. We are using some extra memory to store address of next node, but apart from that there is no other major disadvantage. I'll stop here now. You can write rest of the functions like front function to look at the element at front, or is empty function to check whether queue is empty or not yourself. If you want to get my source code, then you can check the description of this video for a link. So thanks for watching.